Okay, I just wrote that we will wait for a few minutes, but all the sessions, parallel sessions finish. So I want I like to see all of you here, and just we will start new special sessions. It will be devoted slightly different from our presentation thematic. So this is the instrument to see the structure of materials, and we have two talks, one devoted to the photon technique, another one to the neutron spectroscopy. So the first talk is devoted to SKIF Novosibirsk storage ring, and the speaker is Anton Bogomyagkov from the Butkin Institute for Nuclear Physics.
Good afternoon. My presentation is about synhrotron radiation light source, which we are building in Novosibirsk. The name SKIF is a Russian acronym of Siberian Circular Source of Photons. It is also a name of the nomad people that lived in Siberia a long time ago, Scythian. The pictures over here are the views of Novosibirsk and a place where the SKIF is going to be built. The slide over here gives you a brief overview of synchrotron radiation source parameters, which is designed to have a beam energy of 3 GeV with a circumference of less than 500 meters, which is a small parameter. The natural emittance is less than 100 picometers that makes this accelerator a fourth generation light source. Dynamic aperture is optimized and sufficient enough for traditional off-axis injection and for usual injection complex. We have a sufficient number of beam lines from wigglers and delectors. We have strong field dipoles to produce hard X-ray, and of course we have weak field magnets for soft X-ray. And basically the project is very simple, robust, and used proven solutions. Here you can see the general sketch of the facility. It starts from a linear accelerator with 200 MeV energy, following by booster ring operating at 1 GHz frequency with energy up to 3 GeV, and the main ring, which possesses a 16-fold symmetry with a natural emittance of 75 picometers. In order to make the construction faster, the injection facility over here will be built first. This is a Google picture, satellite picture of the map. So you can see the Novosibirsk city over here, and the downtown is approximately here. This is the Ob River. Over here is the Butkin Institute of Nuclear Physics, and this is a site for SKIF, which is about 20 kilometers from Novosibirsk downtown, and international airport in the left corner. The place for SKIF is basically a greenfield by a small town Koltsovo, which doesn't have any heavy industry, and therefore the ground is very stable, no mechanical vibrations, no interference with other facilities. It has enough, it has a power station which provides enough electricity, and there is a developed infrastructure like roads and other things over here. The slides here show some designs, how the building will look like, and this is the blueprint of the site. You can recognize the building for the main storage ring. These two buildings over here for injection complex. All of that is being built right now. Here you can see the optical functions, the super period of the accelerator, and the whole lattice is made of 16 super periods like that. The beam energy is 3 GeV. The natural emittance is 73 picometers. And the super period starts from the center of the straight section where insertion device, where the synchrotron radiation will come from, and it ends by the other end of the straight section. This is how the designs look in 3D. You can recognize the 5 unit cells and a matching section, which starts and finishes the straight section, which is dispersion free. For the chromaticity correction, we use only 2 families of sextuplets. We don't use any other multiples, no additional harmonic sextuplets, which is very beneficial for dynamic aperture. The whole lattice linear optics was optimized to increase dynamic aperture, and you can see parameters of the sextuple that they are feasible, not so strong. The pictures over here show scans of dynamic aperture. The left one shows horizontal dynamic aperture represented by color. The star point over here shows a working point in Betatron tunes. So we chose the working point that provides the horizontal dynamic aperture about 12 millimeters. For vertical plane, dynamic aperture is a little less than 6 millimeters. And the right plot shows you dynamic aperture with maximum energy deviation. So you can see that it reduced from 12 millimeters in horizontal direction to almost 7. The working point is also chosen to provide minimum emittance. You can see that we are very close to actual one. And it is a compromise between the minimum emittance and large dynamic aperture. Here you can see survival plots. So the red color represents the particle survived 1,000 turns. Basically, it's another measure of dynamic aperture. You can see the variation of tunes with respect to momentum deviation, and you also can see the different dynamic apertures for different sets of misalignment errors in the lattice. So we plan to have 16 straight sections. One of them is designated for RF cavity, another one for injection, and the others for installation of insertion devices. And the users required different type of insertion devices with different values of the field and a period and of the device. Each of them will emit a different power. And optical functions were optimized in such a way that installation of each device doesn't disturb the emittance. So for bare lattice, emittance is 73, installation of one undulator slightly changes it. Installation of one wiggler is almost the same, and it's true for 3 wigglers also. And you may see installation of the wiggler will disturb the linear optical functions. This is a disturbed picture, and it is possible to correct, and it becomes as before on the right plot over here. For the straight section, we have 2 variants of the optics. The one shown on previous slide uses only 2 doublets, 2 quadruples at the beginning of the section and at the end. If we install additional quadruple, we can reduce the value of the horizontal beta function in the middle of the straight section, and then installation of insertion device will decrease horizontal emittance, which could be useful for some of the experiments. The plot over here shows you the change of dynamic aperture in this new optics with installation of undulator. So undulator doesn't change dynamic aperture, but wiggler will change it, but it's still sufficient for usual injection for a good beam lifetime. We studied influence of intrabeam scattering on emittance and beam dynamics. You can see different plots showing you the ratio of emittance, including IBS, to the natural emittance with respect to beam current. So the natural emittance, the starting emittance is 73 picometers. If we use 10% coupling and only one RF, we will have emittance of 100 picometers with a beam current of 100 milliamp. In order to decrease emittance, we plan to introduce a search harmonic cavity, which will make the bunch longer, and therefore emittance from 113 will decrease to 90 picometers, and the vertical is 11 to 9. If some users requested operation at 100% coupling, that allows to reduce emittance even further. So both emittances, the ultimate case, become a little less than 50 picometers. We studied intrabeam scattering with insertion devices, paying attention at the geometrical brightness for two wavelengths of 1 angstrom and 10 angstrom. And you can see in the table, this is the brightness for installation of undulator with one cavity or with one cavity plus search harmonic cavity. The same set for the superconducting Wigler, and the last two columns represent the ultimate case when 10 superconductors, undulators, and 2 superconducting Wiglers were installed. And in the ultimate case, we have emittance around 80 picometers with a brightness of 86 at 1 angstrom wavelengths. So for the bare baseline lattice at 400 milliamps in 510 bunches with 10% coupling and 3% energy acceptance, which requires 0.8 megavolt of RF voltage, horizontal emittance increases from 70 picometers to 113. At this operation mode, the Tushik lifetime is about 3 hours. If we introduce the search harmonic cavity, which will increase the bunch length 3 times, emittance will drop to 90 picometers, and the Tushik lifetime will increase almost to 8 hours. If we use 100% coupling, then emittance become around 50 and 60 picometers, equal in both planes, with about 6 hours of lifetime. However, the brightness is lower about 2 times for this wavelength range. In the premium configuration, the Tushik lifetime is about more than 5 hours. RF voltage is 1.4 megavolt. We need to include coherent losses and other collective effects. In the premium configuration, elongating the bunch and using the 10% coupling, we have an 80 picometer emittance. The maximum geometrical brightness in the wavelengths from 1 angstrom to 10 angstrom is reached for coupling between 0.5 and 5%. We studied how to, we studied influence of misalignment errors. So we can see alignment errors of quadrupoles, sextupoles, dipoles, and girders. And we studied how to correct the closed orbit distortion. And you can see that without correction, the orbit deviates, shown by blue line, almost by 2 millimeters. After the correction, it's close to 60 microns. In order to correct the orbit, we use about 128 steering magnets, some of them installed in sextupoles and 32 are individual. In order to correct the optical functions, in particular the beta function, we use the gradient correctors which are installed in the sextuplets. And for coupling, we use SKIF gradient correctors also installed in the sextuplets. On the plot over here, you can see a resulting table for different alignment errors, how dynamic aperture changes. And the plot over here shows you 1 sigma envelope of the beam and of the orbit. So optics was well studied and well corrected, and we have enough knobs to correct whatever alignment errors we will meet. We also studied influence of different multiple errors, for example, random quadrupole. This is the different sets of errors, and it shows, each line shows a dynamic aperture. We looked at the how the Betatron changes and how to correct it. And the plots over here shows different cases of errors distribution. Design of the magnets is already almost finished. Some dipoles are already ready. This is a table of parameters. Quadrupoles are done, sextupoles are almost finished. You can see the 3D pictures of design plots. RF system is going to operate at 357 megahertz. In booster and the main range of frequency is the same. For the booster, we will have three cavities. For the main ring, we will have 5. And we will have third harmonic, which will have 3 cavities. That's how the cavity will look like. The vacuum lifetime is more than 10 hours. And the table here shows you lifetime from different processes, from elastic scattering on residual gas and elastic scattering. The vacuum chamber is made of aluminum alloy, and all connections of the vacuum chamber are made similar to Super KB approach, and we use compensators like in PEP2. We have a cryopump of distributed net coating. We have compact pumps in the arcs. And the conditioning, expected conditioning time is around 3 to 6 months. The vacuum system design is already made. You can see the flanges, different blueprints of how the vacuum chamber looks like in different elements, and a quadrupole here. This is the basic profile in the straight section, the profile of the vacuum chamber in the sextuples. The inner diameter of a beam pipe is 27 millimeters, and the distance between pipes is about 1 meter. And I come to my conclusion. So the light source that we designed, the optics of the light source provides a natural emittance of 73 picometers at 3 GeV beam energy with a circumference of 476 meters. We use only 2 sextuple families, which provide sufficient and large dynamic aperture and very good momentum acceptance. All of that is giving us a good beam lifetime and a traditional injection. SKIF has 16 straight sections of 6 meters long. 2 of them are used for injection in RF cavities, so 14 are available for insertion device. Optical functions are optimized to accommodate high field insertion devices. We expect to have 13 beam lights, 14 from insertion devices, 8 from high field permanent magnets. The magnets have a field of 2.1 Tesla. Also, additional 8 beam lines from regular cell magnets with half a Tesla field. We optimize the types of the magnets in order to decrease the cost and to save the production time. All major systems research and development is completed and design is already going. We also appreciate and expect collaboration with different synchrotron radiation laboratories all over the world. Thank you.
Okay, thanks. We have enough time for the questions since we are 8 minutes before the schedule. So are there any questions? Mikhail Ivanovich, you have the microphone on. Do you have the question? I did not see any hands, but I have some questions first. First is connected with the wavelengths. Do you have really some specific request? What should be the optimal wavelengths? Because you use from 1 to 10 extreme. I mean from the users.
That's I don't know how to answer this question briefly. The table over here shows you six experiments which require wavelengths or energy of photons in this range. So you can see the range is rather wide, and therefore we use from 1 angstrom to 10 angstrom. So there are different experiments that require different wavelengths.
So the list of experiments is already exist?
Yes.
Okay. And how many lines you expect to have?
We expect to have 32.
32, okay.
Actually 30 beam lines.
30 beam lines, okay. And another maybe most political or financial questions. What is the real situation with the financing of your project? And when we suspected that you have to receive some money previous year, as I understand, but what is the real situation?
So the government decree was signed before pandemic started. Therefore, decree is already on the paper and different organizations are working with it, and therefore we are not, the financing, the funding is not possible to be cut down at present stage. It will require the change of government decree. Some money already came and the work is already financed. The other money didn't come, and the situation depends on the rules of Russian Federation. Before money is distributed, there should be some tests, some checks completed, some financial checks. And we have negotiation with the government that if it proceeds like they want, then construction time will be longer. And government is understanding our arguments and trying to change and make it faster. So the real situation is that some money came, some didn't, and there is a constant negotiation with the government about making the process smoother.